Hello, and welcome to Rust London Talks. I'm your host, Ernest, and this is our special edition Rust London in ML meetup. Sorry, just move my slide. This is the Rust London community, and we are a part of the Rust London user group. Rust London is a platform and a community that serves the people in London who are interested in Rust. We are a showcase and we are a community of people who provide a space for people to talk about what they're doing with Rust. So both individuals and companies who are doing things with Rust in London, we give you an opportunity to showcase what you've got going on, showcase what you're building, and showcase how you're using the Rust language. The user group was started in June 2014. We are technically the oldest Rust community chapter in Europe, and we're also one of the largest as well, which we're really proud of. We have 3 different events that form our user group. This being the London Talks is one of them. We also have the Rust London Code Dojo, and we also have the Rust London Hack and Learn. Our main purpose is to always be a place where we can encourage people to show off what they've got going on and provide a platform and a stage for people to showcase all of the amazing things they're doing with Rust. Here is a very cluttered slide showing some of the companies using Rust, both in London and wider. One of the really cool things about the programming language is that we have seen a boom in adoption, both from 2019 and also this year as well. We're seeing a lot more companies in the city using Rust in their stacks, and they've moved from tinkering and experimenting with the language to actually really taking it seriously and baking it in to their language. We're actually going to hear from one of those companies today, Emotech, and there are a few notable mentions here as well. Bibbit, who are also a fintech company based in London, and TrueLayer, who we're going to have announce some job roles as well in our community announcements. My co-host and former member of the Rust ML user group, Rust ML working group, sorry, Luca Palmieri, will also be showcasing some of the things that they have going on at TrueLayer and some of the job opportunities that they have. The Rust London community is always focused on making sure that the environment that we have and the environment that we build is as friendly as possible to all levels of programmer. Whether you're just coming from a different user language group and you're just hearing about Rust, or you've been in from the beginning and you're very experienced, we want to build a space for you where you feel comfortable and you feel welcome at all times. And that leads us on to our code of conduct. The Rust London community is signed up to the Berlin Code of Conduct, and that basically outlines how we interact with each other, how we interact with both in-person meetups and also on virtual meetups. The key thing is to always remember to treat people with respect, always focused on being considerate to other people's feelings, and we do encourage robust debate. We encourage people to absolutely share their views and thoughts, but always in a respectful and considerate manner. Please follow us on Twitter at Rust London Users. The hashtag for this event is Rust London. Now, because we don't have any emojis in the chat feature on this platform, it's going to be really important that you all really show your appreciation to the speakers on Twitter. So usually I would encourage everyone to share their crab emojis, their clap emojis as a way of still keeping that level of appreciation from a live event. But please feel free to use the hashtag on Twitter, hashtag #RustLondon, to show your appreciation to the speakers. We also have our YouTube channel, Rust London, where all of the talks will be uploaded, and you'll be able to watch back on any of our archive of videos. Right, so the way we do questions and answers in these events is we use Slido, and we allow you to post your questions in Slido, which will be collated, and then we'll have a Q&A panel session at the end of all of the speakers. So there won't be any questions taken at the end of the speaker's talk. This is to manage time and to also make sure you all stick around to make sure your questions are answered, right? So we'll have a Q&A panel session at the end where all of the questions you have collated will be listed in Slido. So please either use the QR code here or just go to slido.com and put in the hashtag RustMLQuestions, and you'll be able to, without having to sign up or anything, ask a question for this specific event. I'm now going to hand over to Tolu from the ODSC, who will talk about what they're about and what they do. We want to give them a big thank you for hosting us on their platform, and we want to know more about what they do. So take it away, Tolu.
Hi, Ernest. Thank you for that. Everyone, you're welcome once again to the ODSC and to the Rust London meetup. All right, so just a quick one. The ODSC is a community that supports AI and data science, open applications across the world. We have several communities and meetups around the several continents, the USA, in Europe, in Asia, and I'm here in Lagos. I'm in Lagos, Nigeria right now. And so basically the whole concept of ODSC is to promote open source applications that focuses on AI and data science. So as you can see in the next slide, you're going to be seeing several things that we have, we have for those who are going to be joining the community of ODSC, in terms of those who are probably trying to get their hands in data science or probably trying to upskill in data science. So we have several community sessions. Next year we have upcoming ones in Europe and as well as in the US as well. And so we're happy to collaborate in terms of with the Rust ML community, and it's a very good one. So I'll hand over the mic to Ernest. Yeah, thank you for that.
Thank you very much, Tolu. And if you can see my slide here, this is a list of all the upcoming events that they have. I've personally been to one of the last conferences. I was kindly given a ticket to one of their last conferences, and I was blown away by the quality of the speakers, the caliber of the speakers that they had at ODSC West, which was the West Coast, kind of like San Francisco based conference, if I'm not mistaken, Tolu, right? ODSC West.
Yes, definitely, yeah.
Yeah, I was really blown away by the caliber of speakers and the people that were there. You had like half of MIT in the room, so that was like amazing to see. So it's definitely something to check out, and thank you very much for sharing with that, and thank you again for hosting us.
Yeah, you're welcome.
Okay, right, we have some Rust London community announcements that we wanted to share with you all. First one's being some very special job postings. I'm going to hand over to my co-organizer, Luca Palmieri, who is going to talk more about the jobs at TrueLayer.
Evening, everybody. Nice to be here, although virtually. So, TrueLayer is a company based in London, working financial technology, but we also have an office based in Milan, and we've been using Rust somewhat extensively in production for the past 6 or so months. And we're expanding the Rust team even further. So we're currently looking for 2 backend engineers to work on a Rust system, which is basically a core banking engine to manage funds on behalf of customers. So in the parabanking industry, so to speak. If you're curious, if you have questions, just reach out to me either here or whatever social platform you can find me, and I'm happy to answer.
Amazing. Thank you very much, Luca. TrueLayer are our London sponsors when we have in-person events. They haven't been able to sponsor us for a while with their amazing office and pizzas and beers, but hopefully one day soon we'll be back there and we'll be back to how we used to do things as well. TrueLayer are an amazing, they're amazing advocates of Rust. They've been one of the first really important fintech teams in the city of London that have really adopted Rust and really pushed it forward. So we're always very grateful to TrueLayer and very big fans of everything they're doing. There is also more job postings from the Fwumious team. They are a team building a decentralized platform for app developers to build their own sort of meta platforms and build their own royalty models using their Fwumious engine. They were our speakers at our last event where we had a collaboration with the C++ London community, and they have announced a range of job posts for everything that they're trying to build. I was blown away by what they were doing with C++, mixing C++, Rust, and WASM to build their backend engine. And I think anyone who really wants a challenge and really wants to see what's going on right at the cutting edge of Rust and WASM, give the Fwumious folks a look. And yeah, they've got lots of opportunities there. Next community announcement is from our friends at Ferrous Systems. They still have the offer available that they kindly extended to me over our last meetups. Their courses, so these Ferrous Systems is they're the leading trainers in Rust throughout the ecosystem. You actually have members of the Rust core team who are teaching, and they have a range of courses for people who want to get bootstrapped with Rust, going from zero to hello world to actually becoming really settled in the language. So if you are an enterprise, if you're a company and you want to get your team up to speed with Rust, these are probably the best people, if not probably, these are the best people to learn from. They also have embedded courses as well. And at our last meetup, they extended a promo code to me, which gives a discount on any of their courses. So that's still on, that's still running. So I wanted to share that with you all today. So check out their website. These are the dates of the courses, and see if that makes sense to you as a person or your team. Today's meetup, I'm really happy to be hosting the Rust ML working group. I've got to get that right, the Rust ML working group. I've been so surprised by what has been going on in that corner of the Rust ecosystem. And we're going to be having 3 talks from 4 speakers who will be taking us through some of the interesting things being done with ML using Rust. Our first speaker will be Andraz Tori, who will then be followed by Paul and Lorenz, who will be doing a joint talk, and we'll close out with Daniel Mckenna giving us a finishing talk. We'll then have the Q&A panel session at the end before we close. So please, if you can go to the hashtag RustLondon and show some kind of appreciation with your memes, with your emojis, just clap where you are at home as much as you can. And please welcome our first speaker, Andraz Tori.
Hello. Please give me the screen sharing option. Super. So I want to check if everybody's seeing the first screen. Yes. Okay. Thank you very much. So hello, I am Andraz Tori. I had recommendations in data science department at Outbrain, and today I'm going to speak about a software we've released as open source called Fwumious Wabbit. So we'll have a short agenda. First, we'll look at the machine learning use case at Outbrain. Then how the software came to be, what was its story. Then we will look at its architecture and some tricks that we use to achieve really top performance in machine learning, and some thoughts unsolicited about the use of the Rust in this use case and what would be like the dream features of Rust in the future. So let's start with where do we use this machine learning? So at Outbrain, we do recommendation systems. And you can see kind of the technology and Rust in action if you open CNN, for example, and you scroll down below the article a bit, and you will see recommendations, recommended stories. Some of them are paid, so publisher and us gets paid if a user clicks on them. Some of them are organic. They are within the publisher's site or sites to kind of produce recirculation. And our job, the data science department at Outbrain, is to figure out what to display here. And for this specific use case that we're talking about today, you can imagine that somehow we have only 500 paid stories and 500 organic stories to choose from. And we need to answer, like, what will we recommend in one specific page view that's happening in real time. And what we're optimizing for is either engagement, so clicks, for in the case of organic, of the traffic within the publisher, or highest yield, so the highest publisher's kind of outcome revenue that happens if the user clicks. Now, I want to stress the need for speed here. Our scale at online, serving thousands of publishers, I did like back of the envelope calculation, and we do about 100 million predictions per second. Individual predictions, what's the chance of this user opening this page right now, clicking on this story. And we update our models every few minutes. We do incremental learning, not once a day, not once an hour, every few minutes. And this is the online use case. And you can imagine this is like if you manage to squeeze some more predictions through, you either increase your revenue or decrease your system resource usage. The other part is, of course, data science before you build the models. And our typical research data set is like 300 million records, and each record has 50 features per record. Features in data science are basically properties or attributes of records. So this at the end comes out to be like an, I don't know, 100 gigabyte kind of input file compressed. And important to know is, why are we willing to invest so much into it? This is the economic engine of the company. The better we do, the better publishers do, the better we do. And I want to speak a bit about AutoML. So machine learning is being automated, and everything that can be automated is automated out of the hands of data scientists. And it's really a spaghetti throwing competition. So you hit the spaghetti against the wall and you see if something sticks, if something performs better, using some feature differently, some hyperparameter, etc., finding different neural architecture and similar. So the faster you can throw, the better you can be, and the better your business can be. So ML being fast really matters. So we were using a piece of software called Fwumious Wabbit. And this is a very kind of, I would say, even legendary machine learning toolkit that was initially developed at Yahoo. Now its authors are at Microsoft. It's still being developed. And it's very high performance. It has really good ergonomics for the AutoML use case. And it supports this fully online case that we have, like enormous throughput and updating the models all the time. And we were using this for a while, and we were very kind of familiar with the C++ source code, how it works and all that. And before somebody asks, yes, we did use TensorFlow, or we tried it, we use it on a portion of our traffic, but it's order of magnitude slower for our use case compared to Fwumious Wabbit. So we started to hit limits of this software. So first, we started to use more advanced machine learning. We were using logistic regression, and we started going into the factorization machines. And we had the nagging feeling that this is fast, but maybe we can make it much faster. And this was depths of deep COVID times, April 2020. We had this idea of very narrow toolkit for some very specific use case in machine learning, maybe using, you know, some low-level software. Most of Outbrain otherwise uses Java or Python in data science, right? So what to choose, what happened. So Fwumious Wabbit was born, and we basically decided to take very clever WOWPAL architecture. I'll explain about it a bit later. I started to learn Rust from scratch, and I was doing this project like over the weekends, free time between Zoom meetings. I was moonlighting. My primary role is being a manager, so this was kind of going out of the way to be really hands-on. And the goal was very simple, like drop-in replacement for this previous tool, WOWPAL, which means complete compatibility in command lines. Basically, for the use cases we were using it, the same command lines work, you just change the binary. Complete compatibility even in predictions. You know, you throw 100,000 examples to WOWPAL, you throw 100,000 examples to Fwumious, and the goal was to have 100% to the 10 decimal place the same predictions, which was really a very interesting challenge, but also a superpower, because you basically had a primary implementation that you had to kind of match and avoid bugs through that. But I want now to get to the architecture and the interesting things. So the first thing is that WOWPAL Wabbit was optimized for kind of AutoML in a way. It's optimized for going through the same data sets thousands and thousands of times. And it creates something called example cache, or structure that kind of parses the data set into something that's extremely efficient to then pass forward to the, let's say, mathematical stage of the software. It allows recombinations via command line parameters like Cartesian combinations of features, etc. It also has the hotpath for most common use case in cases like ours, which is like all features are categorical and all have the value of 1, so they are binary features. And in some problems this is true. In ours it is. There are very few features that are different, and there is basically a hard-coded code path for that. And it uses something, this was kind of WOWPAL's innovation 10 years ago, called hashing trick, which means a single parameter space in data science. Everything is kind of thrown in the same bucket. Some things overlap, but who cares? On average, it works if you have a really big space. So I'll speak now about architecture and then explain some interesting things about each piece of it and how we maximize our kind of performance using Rust capabilities. So the architecture is really in 3 stages. You get the input file, you parse it in this super tightly packed cache file that can be easily used by next stages. So you can imagine this is text file, this is kind of human readable, something similar to CSV, and this is super optimized for specific use cases, and this is saved to disk. Then you have basically feature combiner stage where you can pass to WOWPAL and Fwumious, like use features not others, you can model interaction. And this creates then a very simple feature array of basically just floats. Actually, U32 hashes plus floats. And then the final stage is basically regressor. This is really the mathematical stage that starts building models of each individual example that comes through. It updates the weights. Usually, I don't know, we have the model size about 1 gigabyte, and then it makes predictions. So we'll go through all these 3 stages and show an example of Rust in each of them. So first stage is the parser. This is basically parsing from the human readable format to something more optimized. So the first interesting thing architecturally is that what you do is that immediately you parse the categorical feature, so 0 and 1 binary feature, you just hash it to a 32 or more precisely 31-bit hash and store it for later use. So you never again deal with any string, with anything. You just, every feature is now just a hash. And you also, if you happen to have a value, you also save it. But in most cases, the value is 1 because most of the features, and I'll explain about some of them later, in this type of logistic regression problems are basically binary. Some are continuous, and most features also are not kind of multi-valued in a sense of, usually you have, you're looking at page with this URL, and that's the feature, while that URL might have multiple categories. Maybe it's news and it's politics. but those are like more rare cases. So you really write the code to optimize for the common case. And for those dealing with TensorFlow, you know about TF record. So this is kind of TF record on steroids for a very specific use case. I'll go like a bit hardcore here to show the actual kind of structure of the buffer that gets created. So here we have like feature A that has one value or one member that has implicit value of 1. So binary feature, let's say it's a string F1. And then feature B that is kind of multi-feature, it has multiple values, and one is F2, binary feature, and the second is F3, string of F3, that has a value of 0.5. So it's continuous feature in this case. So what's the output of this parser? How does it present it? So first is, because of the later stages, you want to very quickly get to the all features A and all features B. You have the first part that is kind of the directly addressable table. So you always know at exactly which index you will find that feature. Very, very, very single step. And then there is basically the hot code path or the common case where it's binary feature of value 1 and just the single feature. So you can just store it in place. If you decide that 31 bits of a hash of describing where that feature lives in your feature space is enough, you basically use the first bit to indicate whether this is kind of the simple code path or not. And if it is, you just store it in place. If it's not, like in the feature B case, you basically store a short pointer, 15 bits, because these arrays are not very long, to where that feature should be read in the kind of dynamic part of the buffer, and the length of how many features there are under feature B. And then this buffer looks like the same, like bit 0 is always 0 here, and then you have 31 bits of hash, but you also have the ability to now to store the value, or 0.5 in this case, right? And so this was F3, you store hash of F3, and you store 0.5. So this is the format. Now, where does Rust come into play here? Very kind of, if you want to deal with this format very, very quickly, you can use macros to basically embed your code into different code paths. So if you're now reading from this array and you say, I need to read feature from the record buffer, this is the record buffer, I need to read feature index 1 or 2 or 0, whatever, and I want something to be pulled there, like hash data. So in this case, the hashed index. I will use this macro across the code to do that. And what this macro does is basically it says, look at the first bit. If the first bit is kind of this complicated feature with either multiple values or continuous features, then you decode the start and the end index, and you go through them, read out the feature, and call the code block that I passed to the macro. And if it's not, I'll pass the other code block to the macro. So really, if now there is this, you can imagine now that actually this macro, you're striving to be a very, very simple operation also. So when Rust now goes and optimize this, it can really optimize the heck out of it. You can also generally use inline functions here, but it was pretty nice to do this with macros. So this is one thing where we use macros across the code base to do this kind of tricks where we want the specialization. We have two slightly different code paths, and then they have to include the same block. We just use macros to make Rust specialize those. So that's an example from the parser. Now let's go to the future combiner. So future combiner is the one that really calls this macro often. What feature combiner does, as explained, if you have feature A and feature B, and you say, hey, I actually also want the Cartesian product of these features. So create me new features that are just the combinations of those features. So generally, if you would just concatenate them and then hash them, you would get F1, F2. So F1 from A and F2 from B, and then F1 and F3, F1 from A and F3 for B. But because you're kind of hashing everything up front, you can basically say, look, I can just XOR those two hashes. I don't need to, again, go concatenate the string and then hash it, etc. I just use XOR. It's slightly more complicated, but basically it reduces everything to this kind of operations. And the output of feature combiner, as said, is a very simple vector of just the hash index. So where should the mathematical stage be looking for this weight of the feature in its model, and the input value of the feature, which is like continuous value. In most cases, as we said, it's 1, but in some cases it's different. It is continuous value. And then after you do all this, the regressor in logistic regression case is completely oblivious to where the features are coming from. It's completely generalized. So let's now look at the regressor and some tricks that we did there. So first to know, for those that are more on the Rust side but not on the data science side, logistic regression is really fairly simple algorithm. The prediction step is super simple. You basically, from the previous step, you get all these hashes of features. So you now know where in your model those floats that represent the weights of those features live. And you basically just take each one of them, multiply by either 1 or continuous value of the feature, and you do a sum, and then just do logistic function over it. It's really tight, simple loop, like you. And it's interesting that this is the workhorse of many like high performance, high velocity machine learning tasks. Like in CTR prediction, click-to-rate prediction, this was the workhorse for 10 years. Now let's look. First thing, this is not really Rust related, but because this loop is super tight, you would say, look, there's nothing. You can maybe vectorize it, but after you actually do disassembly and look at what's happening, you do profiling, you start noticing that it's not actually the math part here that's problematic. It's the fact that you're basically doing random memory access across 1 gigabyte from memory all the time in a kind of the core loop. So you're actually being, despite all the branch predictors and all that, you're being stopped because of the memory latency. So this is not the real comment, and you will see that I'm using a lot of how to say. I'm playing hard and fast with the syntax, a bit of Python here, just to explain what's happening, because Rust would be a bit more verbose, as you know. But in Rust, you have pretty easy access to basically and you can see I actually call the prefetch instruction within that loop to prefetch me the most random from eight cycles of this loop later. And you know, this is horrible from Rust perspective. You're doing basically get unchecked. You have no clue if this array actually is that long. But the good thing is this prefetch, at least on Intel processors, is basically a function that has absolutely no side effects except that it sometimes preloads that from memory. So you can call it for any memory address, and the processor will just do it or not. It's an advisory function, but you don't need to care about safety. So this is kind of contra Rust approach, which is really interesting, because when you really get to the low level, you need to start thinking about which unsafe things in your specific use case are still safe. Let's go on. So next we said, okay, I was talking now about logistic regression, but we're really interested in factorization machines. Factorization machines are kind of a much more advanced version of machine learning. It's like halfway to neural networks. You basically create embeddings around features, and the good thing about them is that even if you never seen some interaction between, I don't know, specific publisher and specific recommendation that you want to do, just based on their embeddings, how they behaved in a similar situation, you can have some idea of how it will behave here. So you can predict interactions that you haven't explicitly seen. I don't know if I want to really go into details of this slide, but basically for example, you have a feature campaign and publisher and browser version in this case. And you basically create embedding that for each campaign value and for each publisher value and for each browser value, embedding that combines either with publisher or with campaign. So each feature here actually gets multiple embeddings that are used in kind of this double for loop to get to the prediction. This is really kind of mathematically what it is. It's double for loop. It doesn't really matter so much for what I'm trying. I'll be showing. So the interesting thing how we used Rust here was to specialize. So you now have kind of this double for loop, but then you need to loop through the whole embedding and basically do the operation is really more complex than that, but I simplified. The prediction step is this simple almost. And you need to run it. So now here you have a small loop, usually until 4 or 8 or 16, that is in the inner loop, and this runs like 400 times for each prediction, let's say, or 1,000 times. And what we did was like, look, you want to remove all the if sentences, all the jump comments from the inner loops. So we said, look, there are only a few generally used values of k. And we have a macro that basically takes this FFMK and specializes it into a constant. So this is, again, a macro where it says, okay, let's take this input expression, and this is FFM lowercase k, and let's, for specific values, turn it into a constant and run the code block that we're interested in. And if it's not one of the chosen values, then you do the unoptimized version and then the rest. So, of course, for those dealing with performance, you will say, like, but doesn't Rust auto-optimize, auto-vectorize? Doesn't CPU branch predictor do its job? Like, I don't know. The answer is no. We benchmark this to the heck of it. And you get another 3% from here and another 5% from there. And at the end, you get a lot of these wins, and you get something that's completely different to everything else that in terms of performance that we've been able to see. Another and the last kind of optimization, this is not Rust specific, but it's also interesting low level. So in the inner loop of all these things, you usually need to do something which is called an optimizer, like calculate how much you want to update your parameters. And in the optimizer that we use, it's called adagrat, adaptive gradient. You need to run this function. You have some learning rate, which is a constant. Well, it's not a constant, it's variable, so it cannot be used as an immediate in assembler. And then you have 1 divided by S square of something, the errors on that feature that happened. So you need to do this very, very frequently, and the SQRT operation is not the fastest thing on earth to run. So for those that did low-level operation and are kind of into this, you know that there's a Quake method that very well known. You can find articles about the history of this method, that you can do basically 1 divided by, so inverse square root, very, very quickly with very few floating point operations. And you now have AVX operation also. But what we did was, we said, oh, let's look at the float, how it looks like on the very low level. And the floating point number is stored usually as a sign bit, exponent, 7 bits of exponent, and then mantissa. And what if we just use the 7 bits of exponent and just the upper bits of mantissa, so the most significant bits, and use this as a hash table? And we come to basically replace this fairly complicated, well, fairly, it's not that complicated by standards, but it's complicated thing, by a very simple lookup. We basically take the floating point and bit shift it for a couple of bits to look up into 8 kilobytes of small table. So again, does it matter? What about AVX? Well, I don't know. We measured, it does matter a lot. Associated types were also really nice because it allowed us to specialize kind of the models based on how much additional data they need from the optimizer. I won't go into details here. Another optimization we noticed was you sometimes need some temporary buffers, and you usually allocate them on the heap. But if you're again using them in a very tight loop, having those buffers addressed statically on the stack actually again gave us another few percentage of the total runtime improvement. So we again use the Rust code. You could also do inlining here. Well, actually, I don't know if inlining would work perfectly, but you have basically the same code that's run. This is kind of a beefy inner loop. But in one case, it's called with the data structure that lives on the stack. In the other case, it's called with the data structure that lives on the heap. And the heap is basically dynamic, etc. And the stack is used for when the kind of usage of the memory is slower. Yes, and of course, because we know what we're doing, we don't do initialization and all that. So this also helped, another couple percentage. Other tricks we used, we of course carefully profiled everything, used the fastest gzip library, LZ4 whenever we can compress. If you need compression for kind of real-time use cases, this is the fastest. Rust flags, of course, and stupid things like a lot of times like originally Wolfpack wrote the prediction for each 100 million predictions it did, but when you're doing like an AutoML use case, you're really interested in just the last 20 million your evaluation data set. And after you go into all these optimizations, you start to notice that just formatting float to the string to the output is actually taking you quite a lot of time. Anyway, what didn't work, we did some experiments with rolling out our own manual AVX2 code, couldn't improve things. Full data-oriented data structures didn't, and auto-vectorization didn't really work all that well. So the final slides, Rust for Fwumious Wabbit, my kind of final impressions. Easy specialization is really a killer feature. You can do amazing speedups. The downside of it is that actually disassembly isn't working quite so well when you're using lots of macros. I'm sure this is going to be improved eventually. Forced correctness, like when you compile the code, it's usually the right code. And it's not working so well. It's really optimization story for us. If you don't but it's most non-existent, like operation reordering, these fuse multiply add instructions and stuff like that. The compiler just doesn't do them automatically. So compile times weren't an issue because of the small code base. Now, for the last thing, like dream features. Dream features would be like kind of speculative optimization of dynamic traits. So you have something that takes a dynamic trait, but you would like, again, to have hot paths transparently or kind of in opaque way, just optimize. I want optimized compilation of this specific use case, and for the rest, sure, use dynamic traits. And the second thing, which is even more crazy, would be kind of compilation of specialized code on demand. So if you could take half of the program and say, only compile it, kind of embed the compiler into my code and compile it when I already have all the constant parameters I want to compile it with. And for the summary, this is Fwumious Wabbit. If you want to use it, it's on GitHub. It's, I think, really, really fast. If you go and search for a comparison to Wolfpack Wabbit of TensorFlow, of Spark, ML, of all kinds of stuff, you will find articles that basically say, oh, you know, Wolfpack Wabbit is 10 times faster than everything else out there. And in reality, we made our thing even like order of magnitude faster than Wolfpack. So when you really need performance, try it out. And even if you don't, it's a cool thing to play with. But the catch is it's very, very specialized. For what it does, we're happy to accept patches, of course, but it isn't a general machine learning toolkit. And that's that from my side. I would like to thank you very much. Drop the questions here, and now I will be transferring the presentation to Paul. So make presenter. Go, Paul.
Thank you very much, Andraz. Thank you very much for that amazing talk. I just wanted to also state if there was some issues with the sound, the audio, I'm going to try and see what's going on with that, but apologies for that if there was the low encoding and it started to crackle a bit. We're going to try and rectify that, but thank you so much, Andraz, for that amazing talk. Really insightful talk. Please, your questions in the Slido, use the hashtag RustMLQuestions, all one word, and we'll collate all of your questions. Make sure that they are addressed to Andraz specifically so that we know that when we're asking the question, we're asking it to him directly. Thank you very much. And now we have our next speakers coming up, Paul and Lorenz, who are going to be giving us a talk on classical machine learning in Rust. Thank you very much. Take it away, guys.
Yeah, hi everyone, and thank you very much for the introduction, Ernest, and the earlier talk, Andraz. Yeah, so as Ernest mentioned, we're going to talk about Linfa. which is a classical machine learning library in Rust. And everyone can see the slides, right? Okay. Cool. Yeah, so short overview over the talk. We'll give you an outline, introduction with motivations, why we're doing this. Then Lorenz is going to take over and talk a little bit about what we're doing, polishing the interfaces in Linfa, and also show you some current case studies. And I'll wrap up again with a summary and where we headed next. All right, so first off, classical machine learning, right? So maybe you guys think, well, isn't everyone doing neural nets these days, or transformers and attention aware machine learning? And I guess the answer is not everyone, right? So yeah, I mean, of course, this is like the hot new stuff, and even it's moving so fast that the CNN, LSTMs, and GANs are already not the hot new stuff anymore, right? There's newer things out there. But like the classical algorithms, so if you think just PCA, SVM, regressions, elastic net, and so on, they still work, and they're oftentimes a lot easier to interpret. And if it's okay for your domain, can also be faster. And like, why take on complexity you don't need, right? If you don't need it. So I think there's still a strong case for a classical machine learning. Might not get all the attention right now, but it's still important to have this in your toolbox. Then I think the next question is, well, classical machine learning, okay, fine, but like, why do we need to do this again in Rust? Like, we already, like, everyone is using Python and data science, right? And we already have scikit-learn. So doesn't that solve everything already? Like, do we need something else? And I think like we just had a fantastic use case, why that might not be the case, right? But we think there's actually more. So for one, we think Rust is really well adapted to be a universal implementation language, right? And with that we mean, okay, so sure, you're using Python to do machine learning with scikit-learn, but actually what is doing all of the hard work is C and C++ and Fortran code underneath, right? That's just the Python is just a shim over it. And Rust can work really well here as well, right? So Rust has the same advantages as C and C++, so could be used. And we think actually like it has some more advantages, right? Because we have this borrow system with which really helps us with correctness and avoiding accidental copies, much simpler than in C++, if you ask me. And it has like these really nice things, right? So so you get this really nice compiler, which has nice error messages and tells you a lot of things. You get IDE-ish features, could still be improved, but still I think a lot better than what you usually see with C++. You get package management, you get nice tools for testing, benchmarking, and so on, right? So we think it's really better suited than the existing languages. Yeah, much nicer, obviously. And then the second use case would be Rust for performance critical situations. So we've just seen an example for that, right? So like these large scale ML applications where you either need to be very fast because you're serving lots and lots of users, or you just have so much data to crunch through that it actually like the performance difference between Python and faster languages start to matter again. And then I think there's also a case for embedded or low memory environments, and of course IoT is a hot use case here as well. So we think there's definitely a use case for doing like a general purpose classical machine learning library in Rust. Then the next thing you might wonder is, okay, right, but why this project, right? Why is now the right time to do this? And here again, we have two answers for this. So, and Linfa has been underway for about a year. Luca Palmieri actually started the library about a year ago. And the reason why then was the right time was that the prerequisites were met, right? So before you didn't really have the building blocks you need to build such a library. And most importantly, I think there's like the matrix libraries. So you want to be able to easily do fast linear algebra routines. And also to some degree, optimization libraries also weren't quite around as much then. And they also need to standardize the interfaces. And about a year ago, I think the dust had kind of settled. And so it was kind of a good time. And also like other things, maybe statistical routines or random number generators or what have you, like more and more of these things are coming online and are readily available. And the second reason we think that Linfa is a promising project is that it's really a community effort, right? So Lucas started this thing at the Rust Fest in 2019, right? So it started as a community effort right away, right? And then eventually handed over the project to the RustML working group. And now it's really being developed by a growing number of contributors. And so we think this is a really good effort. And in a classical machine learning tool set, right, you have lots of tools. Of course, you want them organized around common interfaces, right? So Lorenz is going to talk about this in a second. But other than that, the tools to some degree are a little bit independent, right? So this is a really good project for being driven by a slightly wider community, and which doesn't need to have like this single person who does it all. Although right now this person is Lorenz, and he will show you a little bit about a little bit of code and yeah, how we classify algorithms and organize interfaces around that. So take it away,
Yes, thank you, Paul. As Paul already mentioned, this is really a community effort, and one of the nice things is that Rust can help us in the implementation. And we will now look at 3 different cases. First, about different classes of algorithms, so how Rust can help us to model them. Then how the type system can give us safety and also improves our interface. And finally, 2 examples how iterations can help. So for example, k-folding, multi-class conversion. So the most common class of algorithms are so-called transformers. Examples for this are kernel methods and dimensionality reduction. So for example, principal component analysis, diffusion maps, or TSNE. I have here a small example for a trait. So we are introducing a transform function, which basically takes an object implementing records, and this records is normally our matrix, and then produces a new type T, which are our targets or matrix, or can be whatever we want. If we are now a bit more specific, then we're looking at fittable algorithms, which can learn a hidden state about their observations. So here we're introducing a data set and additionally constraining our targets. The fit function takes the data set and then producing an object, which is our hidden state. Examples of this are decision trees or hierarchical clustering, and sometimes also the B-scan. And the more specific class are those which can be incrementally learned. So in this case, we're also introducing a second parameter, which is the previous model, and then updating the parameter of the model with the data set and producing a new model. This most of the algorithms you know, so elastic match, basically linear regression with sparsity constraint, and also GMM and fast independent component analysis, and also your day-to-day neural network belongs also to this. Yes, these can be used in Rust, and if you're now looking at data sets, which is a second important part, so normally you're working with data sets, you want to subsample them, for example, apply k-folding, replace weights, or create an histogram. It's really important that we have a unified interface, so which wraps our data and targets. If you're looking at the code, as already mentioned, data is so-called records to differentiate it from the in-the-array data trait. So we're using associated types for late binding. This is similar to the array definition, that we really can simplify our interface in the definitions, and also introducing the weights, which basically are weighting our different observations in the learning process. The target traits can be either continuous values, this would be regression, or discrete labels, which would then be a classification, and also probabilities. And the nice thing about the Rust type system is that we can choose different implementations for different targets. So for example, if you have support vector machines, and you would predict a floating value, then it would choose SVR, so support vector regression. For example, if you have no target at all, it would choose run regression. So you can really differentiate on your type of which kind of algorithm you want to use. After that, we have also different metrics. So after you predicted some data set and then want to compare that with the ground truth, one of the most common metrics are confusion matrices. So these are for binary and multi-label comparisons, and the confusion matrix is here the entry point, and you can calculate accuracy, which is just the sum of the diagonal divided by the total number of observations, or precision, or also something like the Matthew cross correlation, which describes the correlation between ground truth and your your predictions. And of course, we also have receiver operating characteristics to compare probability outputs for different thresholds, and also a common thing which is called area under curve. If you're looking for regression, there's of course also some implemented, so the common you know, for example, mean square error or the R-square type. Okay, I will now give you two small examples how our iterators can help us in Rust. The first one is for k-folding. I think everybody here should know k-folding. Basically, the idea is that we are dividing our data set into 12 different blocks. One is for the validation, and the remaining 11 are for training, and we ensure that we have 12 permutations where each block is a validation block once. Then training, in this example, 12 different models, doing predictions, creating the confusion matrix, and calculating the accuracy, and then calculating the mean value. As you can see, the Rust iterated system is really helping us to model that interface here. And in the second example, we are converting a binary classifier to a multi-class classifier. So for example, if you have a support vector machine, of course, only can do binary classification, but the iterator system helps us to split our data set with the one versus all method, and then training a different model for each new data set, and then converting that for each label into a new multi-class model, which you can then use to predict your data. Okay. In the second part, I will show you two small case studies, so two small algorithms. The first one is k-means. This was the first available, and as Paul already mentioned, it was implemented directly at the beginning of the Rust Fest 2019. The implementation was performed in 2 days, which is a really short time. And you know, everybody should know k-means. It's classically M optimization and performs hard assignments for the different clusters. And the implementation already showed a huge performance gain from 1.3 times of the scikit-learn implementation. I really have to compare here a 2-day implementation compared to a algorithm which was implemented like over 10 years in a library. And this shows the potential of the Rust language. So you can really have a unified workhorse where you can implement all your algorithms and expect a very good performance whatever you're doing. In the second example I will show you is about diffusion maps. This is a bit more colorful. So the basic idea is that we want to project some data, but not in a linear way, but in a non-linear. What we're doing is we're creating a transition probability matrix M, which describes the probability that we're going from one point to another point. This, of course, has a high dimensionality and is done with kernel methods. And then we're asking the question, where are we after t steps, starting from a node V? And the answer is then projected into a lower dimensional space again with spectral decomposition. So we are setting up an eigenproblem, which we are solving with an eigenproblem solver, and then have projected our input data. A small example from the code. So this is divided into two blocks. First, we're creating the kernel matrix, and then we're creating the embedding. The kernel matrix is sparse. We're only using the nearest 50 neighbors, and we're using a so-called Gaussian or RBF kernel with a value of epsilon of 2, transforming the data set into a kernel, and then creating from the kernel with hyperparameter steps as 1 into 2 dimensions, and finally getting the embedding back. I have also a small example here. So these are nested rings, and it's just a toy example, but you really can see the effect. First, we have just one nested ring, just the inner one. If you're adding a second ring, you can see that the nested ring, of course, cannot be separated linearly, but the diffusion maps are separating them and pulling them out. And if you're adding a third one, which has the highest variance of all 3, you can see that this one is also the highest variance in embedding and is pulled out as well, and you can then cluster them easily with a linear classifier, for example, SVM. Yes, I will now shortly just a quick notice how the eigenproblem solver works. I implemented the log-PCG algorithm for the ND-area lint create to give that back to the community. This is the common algorithm to just calculate a few eigenvalues and their corresponding eigenvectors. And the nice thing is that it's matrix free because we have a covariance matrix in SVD. Yes, and that it just calculates a couple of eigenvalues. So we're not interested in the full spectrum, but only the first couple of. And the author of the algorithm also did a nice collaboration. So he supported me in the development and answered some questions I had. Okay. We will now come to the summary. So Paul will take over again, and he will explain a bit where we want to go with Linfa and what is the current status and what kind of algorithms are available.
Yeah, right. Thank you, Lorenz. Right. So as Lorenz already mentioned, we have, I think, quite a few of the basic algorithms together. So quite a number of clustering algorithms, k-means, Gaussian mixture models, DB-scan, and optics. I believe there's currently still a PR out for. We have support vector machines, reduction algorithms such as PCA or diffusion maps, and also kernel methods. We have logistic regression. We have a decision tree implementation, hierarchical clustering, ordinary least squares, and generalized linear models. Elastic net, we still have a PR open for. Fast independent component analysis and Gaussian naive Bayes. And ensemble algorithms, random forests are still PRs for open. So this is already, I think, an impressive list for something that started to come together just a year ago. And indeed, like if you look at our roadmap and let's say you include the things where we have PRs open for, which usually are fairly well along, we've really made good progress on this roadmap, right? So we've ticked a lot of these boxes. So that's great, right? Yeah. but also obviously we're far from being done, right? So there's still lots and lots of things to do. So I think unfortunately it's also fair to say while we do have quite a few algorithms already, most of them kind of like implement like the first version of this algorithm, right? So if you look at scikit-learn, for example, you usually have like lots of different options to choose from. You have different optimizers or different specializations, and oftentimes we don't have all of these, right? So maybe there's also discussions of which we should actually have and if we need all of them, because obviously scikit-learn has grown over time and maybe some of these things are obsolete now, but I think just looking at the list of algorithms doesn't quite do it justice either. I think what we could also do a little bit better is having more thorough tests and driving things really more from end to end, which is not to say that there are no tests or things are incorrect as they stand, but I think it's probably fair to say that we haven't hammered out all of the bugs. And I would definitely say, like, if you're going to use this in production, like, you should be a little bit careful still. But you know, you have to start somewhere, and I think we've made good progress there. Lorenz is, or has done some work, as he's shown you, to kind of unify interfaces and finding kind of like a universal way of expressing different problems and entities. But we're still in the process of unifying the library and polishing these interfaces a little bit. And obviously, we also need much better documentation, right? So most of our algorithms have like a short Rust doc, and that's it. And a much better documentation would be great. In the Rust ML working group, there's talk about doing a Rust ML book, and that would be obviously fantastic to have and great for us to contribute and kind of show off what we have as well. And yeah, it would be very nice to get some real world use cases or real world experiments, which really drives this library through its paces, and then maybe like discover some improvement opportunities, let's call them. But yeah, gives this thing a real showcase. And with that, I would like to thank you for your attention and for yeah, looking into this. And obviously, we would also like to thank all of the contributors who've contributed. I think there's already 4 contributors with us today. And again, it's a community effort, and I think it's something that is very well suited to a community effort. So if this makes you want to take a look, step up, and contribute a little bit to it, you're very welcome to do that. Once again, direct your questions at Slido, and we'll be happy to answer them after the next talk. And with that, I think I'm handing back to Ernest.
Thank you very much, Paul. Thank you very much, Lorenz. Thank you very much for your very insightful talk. That was filled with lots of very interesting points. What we are going to do now is I'm going to switch and take a little bit of a break. We're going to have a 5-minute break before our last speaker. Everyone, please make sure you direct all your questions to Paul and or Lorenz using the Slido QR code or use the hashtag held up here. We're just going to try and work out a few things. So please keep your questions coming in. And we're just going to take a very quick 5-minute break before our final speaker, Daniel Mckenna. Thank you very much. Just before we do that, I also wanted to mention, which I forgot to do in my opening address, please follow the Rust ML working group on Twitter. I'm going to switch to my slides now, and I'll have the social media handle for the Rust ML working group on there as well. So if everyone could please follow the Rust ML working group on Twitter as well, that would be amazing. Thank you all. Hello, everyone, and welcome back. Welcome back. It's great to have you back with us. We're now going to have our final speaker, Daniel Mckenna from Emotech. And here you go.
Cool. And shut this window.
Great.
So, well, I'm Daniel Mckenna. I'm going to be giving a talk about multimodal pronunciation assessment with Rust, which will also explain what all that means. So, about me, I studied artificial intelligence at Reading University. I started using Rust around about 2015-16. Previously, my day job was mostly C++, C, occasionally Simulink. I'm probably most known in the Rust community for cargo tarpaulin and maybe to a lesser extent ND array vision. And on most platforms, I'm XD009642. So you can find me there if you want to contact me and ask me any questions afterwards. And Emotech, who I currently work for, is a London startup founded in 2014. And we look at ways of exploring how we interact with technology and new ways using multimodality and AI in domains such as education, home assistance, and various other things. We collaborate with academia, and we're going to start doing more open source in the near future. And in 2019, we built the first multimodal AI education solution. And currently going forwards, all of our new machine learning systems are currently in Rust and are being written in Rust. So I'll also talk a bit about some of our experience with that. So what is multimodality? So if you come from a control systems background, you'll have an idea about sensor modalities. It's a form of perception, and traditionally combining different modalities would be done through things like Kalman filters and would be for like estimating position using gyroscopic accelerometer, GPS, and other sorts of sparse, well, small features. And it wasn't really feasible for things like image and audio because of the vast amount of data. But advances in deep learning and just generally AI has actually made it practical to start looking at things like multimodal solutions for source and neural network based systems, combining things like video and audio to try and come up with a better understanding of the world. So this is sort of the start of shifting from single modal, just text, just audio, just images, to combining all of these to try and get a richer semantic understanding of what's happening and come up with better solutions. So why would we use this for pronunciation assessment? So audio is crucial for accuracy. If you want to know if someone's saying something correctly, it's best to listen to them. But lips help us also understand. So we have phonemes, the smallest discernible unit of sound that the human sort of makes when speaking. But we also have something called visemes, which we can see in this image I've stolen from Google. And we can see that for different shapes, so viseme from the visual shape your mouth makes when you make the sound, we can see from the different shapes of your mouth, they're also tied to different phonemes. So when you're in a classroom environment and there's potentially background noise, the sort of visual side of the system can help it become more robust to noise and help it perform better, which is obviously useful in educational scenarios. Also, it adds an extra level of feedback. Not only can we show the sounds that people should be making, but we can also show the shapes their mouths should be making, which can especially help when a student may be trying to tackle a sound when learning a language, which isn't very present in their native language, like French people trying to use the letter H. So I've just got a short video of it in action, which, if it wants to play.
I ran to the bank.
I ran to the bank. I ran to the bank.
Ran to the bank.
So I'll just stop it there because the rest is the teacher platform. So you can see that we can take in a transcript and a video and we can oh, for God's sake. And we can take a transcript and video and we can locate where the user says it, and we can give them scores on how well they've said it to the phoneme level, allowing them to click on words and phonemes and hear them again and compare them to a reference teacher. So how do we grade pronunciation? That jumps a slide ahead. How can we grade pronunciation? So there's a few different things, and what really matters with learning a language and pronouncing things is your ability to communicate with other people. So there is pronunciation and goodness of pronunciation and how close the phonemes and sounds you make resemble the sounds they should be. But there's also fluency, which is a measure of how smooth the speech is. Is the rhythm natural? Are there weird pauses, which could affect people's understanding? There's also completeness. Are words being dropped or potentially inserted? And I mean, aside from all this, which we offer, there's a lot more solutions and sorts of metrics that can be used. For example, intonation. It's more useful for tonal languages like Mandarin, where intonation can completely change the meaning of a word. But we also use intonation in English to communicate. We add an upwards inflection at the end of questions, and that's a useful indicator to someone you're speaking with that you've asked a question and not made a statement. But of course, the more metrics we add, the more it can hamper user experience and the more confusing it could be for educators and potentially students. So all of this is driven by customer demand and also delivering a satisfying and useful user experience. So I'll go a bit more into fluency, because fluency is slightly more complicated than pronunciation and completeness. It's got two metrics, rhythm and cohesion. Rhythm is about, do the phonemes last the correct length? So English is a stress time language, so the time between stresses when you speak is pretty much constant. Other languages such as Mandarin are syllable timed, so they actually split up syllables evenly by time. So this is something which someone switching from a syllable time language to a stress time language can struggle with. So this is something we also offer. There's also more time languages which are just fancy syllable time languages, but we'll just ignore them. And as I mentioned, cohesion before, are there gaps or pauses during a word? Has the word been broken up in a way that could impact someone's understanding? So how do you do this in software? So we take in the recording and a transcript. We can work with both video and audio. You normalize and tokenize the transcript. So you want to make sure that things like years are said in a natural way, 1995, not 1995 or 1995. And when we have this corrected transcript, we convert phonemes to pronunciations. So a word can be pronounced in many different ways. For example, scone or scone. So we collect these different candidates' pronunciations to allow us to sort of more fairly assess the user. We don't want to penalize someone if they've used a slightly different accent for doing something like Rossic / non-Rossic sounds, path and path, etc. We then sort of take this, get the phonemes for each time slice, well, the likelihood of each one, and using dynamic algorithms, we work out the likely routes through the pronunciations. And this gives us the start times and end times for phonemes and words, and turns this into a hybrid system. So it's not just neural networks, there's also some classical statistics as well involved. We can then use the likelihoods and the timings to work out the quality of the pronunciation, and from that we can start to work out fluency. And we're currently using TensorFlow for inference. So why is TensorFlow painful for machine learning systems? There are some reasons. I mean, it's a great library, but it does have some issues. So Python, the main sort of realm in which researchers work, doesn't offer the performance needed for production, especially when you care about returning results quickly. You can try and move it to C++ using TensorFlow serving, but it only works well really with simple inputs. You'll still need services on either end to do things like format conversion for various video formats, reject bad samples for bad transcripts or videos which are unusable, like less than a certain frames per second or with no audio. And as you have more neural networks, you end up with a microservice explosion, where you end up with a lot of different services for something which really makes sense in one cohesive service. So because I knew C++ before, and because other Emotech engineers use Go, we initially looked at the Go and C++ bindings for TensorFlow. So the documentation is lacking for both. There seems to be little stability guarantees, and it doesn't look like these are designed for users particularly. There's also Basel issues with TensorFlow C++. Other C++ libraries that we use from Google also use Basel, but TensorFlow is on a pre-1.0 version, 0.24 to 0.26, if I recall correctly. And it doesn't overlap with the other libraries we use that use Basel. They're disjoint, and it turns the build system into a bit of a nightmare. There's also, as another minor pain point, no C runtime distributed between TensorFlow 1.15 and 2.3, so everything in 2.x before 2.3. That's not really so much an issue for C++ and Go, but it's more of an issue for Rust TensorFlow bindings. There's also contrib modules, which are painful. When you import TensorFlow in Python, it walks over the contrib folder looking for any shared object and calls tf-load library. This is one of the reasons TensorFlow takes so long to start up on Python, and it also makes it very hard to use those modules outside of a Python environment, because you need to either build them with Basel, copy them out of the contrib folder after locating them and put them in your Docker image, and it just turns into a bit of a nightmare. So contrib modules are something we avoid. So why then use Rust TensorFlow? So the C API is stable for 1.x. It's very new in TF2, only in 2.3 and beyond, but it seems API compatible with the TensorFlow version 1, which is great. It seems to be a very solid core that everything's built on. The TensorFlow bindings of TensorFlow are documented in idiomatic. They make use of the C API correctly, modeling the lifetimes and ownership, and providing things like drop impulse, whereas using the C API, which is largely undocumented, you struggle to realize when TensorFlow owns the memory you're allocating versus when you should be cleaning it up, and the order of initialization. The API design also actually answers a lot of questions which I had when looking at the TensorFlow bindings just through the types, which is great. It's really useful as a programmer, and this is one of the big strengths with Rust and its type system. And they also work to avoid breaking changes, which is great if you want to keep upgrading. You don't want to end up stuck on an old version and unable to move forwards because you have a whole load of refactoring to do. So before we go on, some quick TensorFlow tips for production. Warm up your models. TensorFlow graphs are lazy loaded, so the first inference can be, I think it's roughly 3 times slower on our networks, but for larger networks we've used, I've seen it be 5 to 10 times slower, which obviously hammers your 99th percentile latency. Freeze your graphs, so remove the dropout operations, the training operations, freeze constants where it can. That does a lot for performance. and also inference is thread safe. They may not, well, they model this as thread safe in the Rust API, but there is the caveat in the docs where if you're doing any training live, it won't be safe to run inference or do training from multiple threads. You'll need to add something like a read-write lock. But if you're just doing inference, this is great because you can just do inference through multiple requests concurrently and not have to worry about safety because it's safe. So just to demonstrate the point, here's the unfrozen graph performance for one of our networks. We can see that could be a lot of outliers. It typically ranges from 50 to about 120 milliseconds response time. And when we freeze the graph, it suddenly gets a lot tighter. Now the outliers are more about 100 milliseconds, but it's mostly sort of bunched between 60 to 80 milliseconds, which is a pretty good improvement and a lot more consistent, which is one thing that is really useful in production, consistency in performance. So why else use Rust other than the fact it has probably the best TensorFlow bindings outside of using Python, which for reasons discussed wasn't suitable? Well, Tokyo, Tracing and Tonic, and also Warp, which we use, are great high performance libraries for web infrastructure. Porting from NumPy to NDArray is pretty easy. There's even a conversion guide which tells you what the equivalent NumPy command is in NDArray. Serde lets us automatically serialize and deserialize from JavaScript to work with APIs easily. We've got excellent tooling through Cargo Test, Criterion, going to plug myself, Cargo Tarpaulin, and also we were very easily able to deploy it to high performance ARM servers and Intel ones. And the only pain there was actually just trying to build the TensorFlow C runtime. The Rust one just worked out of the box. And also there's faster single threaded speed. So when you're working with a hybrid system, you can't just rely on TensorFlow and its C++ and C underneath to deliver the performance and hope that you don't have to care about what the Python's doing because it's just passing in and out. Instead, with Rust, we can make smart decisions about types. We can create zero copy code. And for an example of this, I mentioned before that words can have multiple candidate pronunciations. So we took a word with one pronunciation and a word with the same number of phonemes, but two possible pronunciations. And we just made two sentences of increasing length of just those two candidate words repeated again and again and again. So here we can see the effect of what happens when the search space grows exponentially to performance. We also removed all the limits for pruning to create the most accurate version of the model. So here's our graph. We have the real-time factor, so the processing time it takes to process the video or audio submitted, divided by the media length, and the sentence length in words. So we can see instantly that the Python one explodes exponentially eventually, even with just one candidate pronunciation. Whereas the Rust one, it's zero copy and it just ends up being kind of like a linked list of slices almost. For two candidate pronunciations, the Rust one eventually falls susceptible to the growth in search space, but around 18 words a sentence, which is longer than a sentence should really be for communication. So it means we can actually push the Rust one to deliver more accurate results because it can actually go much longer sentences without having to sacrifice accuracy, unlike the Python one. And also it's very easy to do certain experiments, which would be harder in C++ and probably impossible in Python. Just Rust specific ones, the Tokyo run threaded runtime was a lot faster. The bytes crate to move large tensors between threads with just an atomic increment did give massive performance gains over our initial and naive implementation, and it was very easy to switch out the system allocator to gemalloc, one which deals better with concurrent allocations. Also, there was much slower resource utilization. So Python libraries, when you import them, like I mentioned for contrib modules, they can do a lot of stuff and actually take up a lot of RAM just at import time. Our Python version, even after optimization, still needed 1.7 gig to start and 2.5 gig to be usable being able to service 4 requests concurrently. Our Rust one needs 500 megabytes and then it's good for 4 requests, which obviously brings down the cost of our cloud deployments, helping us save money, which is important as a startup, and also deliver more competitive prices to our customers, so they can benefit from Rust as well. Also, the ecosystem, tracing, as I mentioned before, we use tracing is great for adding debug traces, which give us more introspection to what's happening between model boundaries. It's a lot easier to test than things like C++, because the testing is built in as a first-class citizen. Python bindings are as easy to create as in C++. With Pyo3, I did find some issue with sorts of getting things working with ND array, etc., but I was quite an early adopter, so it's hopefully improved by then. And yeah, I found it as easy to create Python bindings as I did in C++ with PyBind, but I found it easier to share those bindings and easier to give them to other people who aren't as au fait with these sorts of system level languages and get them to use without going through complicated installation steps, which some of these people are researchers. Rust is also easier to install for them than our C++ packages. So it's also nice for me because I have to spend less time helping people do things which take up a lot of time when they really shouldn't. So what would I like to see in machine learning in Rust going forwards? I'd like to see a greater proliferation of open standards, for example, ONNX, the Open Neural Network Exchange, specialized inference engines in pure Rust, so we can actually just take our TensorFlow models and move the graphs into a pure Rust inference engine to simplify build and deployment further. Robust SciPy-like equivalents for when researchers want to use more statistical methods, which Linfa's filling that gap. Alternative to Caldi, if no one's used Caldi, it's a system with its own neural network inference engine built in C++ for speech-based systems, because like Valpol Rabbit, TensorFlow wasn't really suitable for performance, but Caldi's a bit, I don't like working with it personally, and there's already a lot of the prerequisite building blocks available in Rust. It just needs someone to glue it together and fill in the rest of the blocks. So I'd like to be able to move our speech recognition systems to Rust eventually. And for our vision pipelines, which are still in C++, using more traditional computer vision, I'd like to see Rust CV grow more and be a viable replacement to OpenCV and dlib. So once again, if you want to contact me, I'm XD009642 on most platforms. You can also contact me for Emotech specific questions at daniel@emotech.co, and you can find Emotech at emotech.ai. We're also hiring for Rust developers, so if you look on our jobs section, you should hopefully see some things. And once again, here's the slide O question part, and I'll hand back to Ernest.
Thank you very much, Daniel. That was a great talk. Again, all the talks have been really insightful, really eye-opening, and really showing just how much is being done with Rust in the area of ML. Please send your questions over to Slido. We're now going to actually go into that part. We're going to have to do a little bit of messing around to get our screens up, so just bear with us. I want to thank the audience especially for being really patient with us with any audio issues that we may have been having, but thank you all. A big thank you to our speakers. All of our speakers have been amazing, and I can't thank you, the Rust ML working group, enough for showcasing and being our last meetup, our last Rust London meetup for 2020, which has been a crazy year. So thank all of you guys again. We will definitely host you again in the future. We might make it a yearly thing just to keep up with what all of you guys are doing, all of you folks are doing, all of the amazing innovation that's coming out of that area of the Rust ecosystem. So thank you, Daniel. Thank all of you. Thank you, Andraz, Lorenz, Paul. Thank you all for all of the, sharing everything that you're doing. Please send your questions over. Now is the time for the Q&A. There are also questions in the GoToWebinar question section as well that I'll look for, but we're going to have our Q&A section come up as well. We're just going to work that out right now, so just please bear with us.
I also have a bunch of questions, taking some notes along the way, so we can explore some of the aspects of the talks. Interesting.
Daniel, you're still sharing your screen, I think. Or not.
Sorry about that.
Shall we get started?
Right, yes. So if we want to have the first question up, are you going to have your screen up, Luca? I've made you a presenter.
It's easier if you do it because I've never done it.
Okay,
So risk
no worries. I'll share my
that is very high.
Yeah, no worries. I'll do that. Oh, I need to make myself. Okay. Right. So, can everyone see my screen and see my questions?
Yes.
Yep.
Crisp and clear.
Right. So, Luca, if you want to just, after I've asked the question, you can just delete the question off the timeline. Then we can go from there. So,
shall
no,
we get started with the first one from Glenn, which is for Andres, so for the first talk. Yes, if you had the time, what would you do next or to improve things further in your Wabbit library, performance-wise?
So the first thing is already out there as a branch on GitHub. We're making Java JNI bindings. So currently, Fwumious basically allows to either be called via command line or it has a daemon mode. So we use it in online scenario via daemon mode. But we would like to kind of take that TCP connection out of the inner loop also. So we are building the JNI bindings, which means it will be directly callable from Java. Alpha is released. As far as the next things go, things like adding linear regression, which is something we use in some cases, but we don't use Fwumious for yet. And maybe a bit more generalized or a bit more some different or next versions of factorization machines. There's something called attention factorization machines and a few other things. And generally, this goes then towards neural network, like deep factorization machines and similar. So those are the likely directions of the future development. But we are, of course, open to patches. What we count on is the specialization in Rust, using the traits and everything, allow us to add features without hurting the performance of the kind of the core path that we're really interested in.
This one is for Paul, which is referring to the very nice GIF image. Trojan's C, C++, and Rust going into shepherded by Python. Has there been any work in wrapping the Rust ML code and libraries in Python? If not, what is the obstacle?
Yeah, so I think I'll best hand this back to you, Luca. As far as I know, you did some work there in the beginning with a Linfa Python binding, and as far as I'm aware, there's been nothing further, but the main hurdle in that, I think, has been time and focus. So we've focused on other
pretty
things.
much the same.
Yeah,
Like,
but there's so take over, Luca. Sorry.
well, it's quite funny as the question and answer it as well. But it's no, I think the bindings from Rust are really good. There's never been much of an issue in my personal experience in binding it. It was mostly time, as Paul is saying. But in Daniel as well, I've done a fair amount of probably wrapping can add something on the topic. It's the face of who is looking for the unmute button.
Biggest pain points for Rust in ML, or I got distracted telling someone how to get the Slido?
No, sorry, I was asking, given that you've done a fair amount of wrapping Rust models in Python, did you encounter any issue or any obstacles in doing so? Performance degradation or similar things?
I didn't see much performance degradation. It was a lot better than using developing the algorithm in Rust and then giving a single Python method to call into it versus using Python bindings for every function in like something like NumPy or the OpenCV bindings or whatever. The sort of one entrance into the bindings was obviously a lot faster. There wasn't much performance difference, but there was some. And like I said, like getting ND-array to work with, I wanted it to return NumPy buffers. I did have some issues with that, but I kind of just abandoned that and just moved to using nested lists.
Perfect. Let's move, well, once I get to you, Daniel. This is coming from Jerry, who's asking, how does the process of like getting a POC done in Python probably by a machine learning researcher and then actually getting that in production via Rust, how does that work? Is it smooth? Is it troublesome? What's your experience?
So for some of the more numeric algorithms, there can obviously be things like rounding issues. You can't always see if like Python's using a float or a double or what the types are. A lot of things get turned into doubles eventually. So you can get small deviances in the results. Typically they're within an acceptable margin of error, so you don't really care. But for working with audio and video, the machine learning systems are obviously trained using files and they pre-extract the tensors. We stream the audio and video in and start decoding it before the whole thing arrives. So using FFmpeg, piping asynchronously to the process and pushing into the ST in and the STD out. And piping into FFmpeg can cause differences in the frames that are provided with lossy encodings, where it can maybe do a better decoding if it has the whole file up front. And that can give much larger differences in results, which raises some eyebrows. But yeah, mainly it's just the pains of video and audio codecs.
I can also comment on a bit of that. So generally, the something else in research and something else in production in general is not the best advice. The amount of work you need to do to basically make sure that those things really give the same predictions on the same inputs is immense. So if you can avoid it, you should. But when you cannot avoid it, this is also an opportunity for amazing speed ups, as Daniel was saying, and as in some cases we've seen. But then you need to create your infrastructure to kind of verify that the predictions actually match to some degree automatically, because kind of doing human checks in every cycle of development is just not scalable.
Well, touching on that, so making sure that stuff is working, I think we can move to the next question, which is on Linfa. I think that was mentioned as well, but there is, of course, it's not super easy to perform testing of numerical algorithms, and it's like kind of a struggle that goes beyond them being really robust. What kind of things are you looking at to make them more robust? So David is bringing up using another piece of software and the same test bindings to check if it's actually correct. What other ideas do you have at this point in time? Either for Paul or
So I would
Lorenz.
think generally no, because I mean, A, for now we don't have full Python bindings, and B, we're not aiming for API compatibility with scikit-learn. It might be, but I think this is a great idea, and it might be worthwhile exploring if there could maybe be another compatibility layer, even if we don't aim for that with the main API, right? So just one that explores the uses the or exposes this for tests. What we generally do though is, I mean, we do port things from scikit-learn, and then we typically try to port the tests as well. So I'm not saying this is always like 100% port, but we would have to look at the kind of payoff of having another layer to run the test suite. It's certainly a very interesting idea.
That's good. From Giles, and this is open to the whole panel. But what are the biggest pain points of actually using transfer machine learning work?
One pain point for me was the Rust TensorFlow bindings updating frequently. So there was a bit of faff with package config and linking to the correct C runtime, which was mildly annoying. And it's one of the things that often trips up new developers. They miss the bit in the README. No one reads docs.
I would add that one of the pain points is simply Rust is not a language to easily prototype in. Like, you need to get everything correct until you will be able to see the first result compiled. So it's quite hard to kind of do incremental development and kind of just throw something out and fix it later, what you usually kind of is the approach in Python. So that also makes it a bit harder, but so I think it's for specific use cases, it has tremendous advantages, but if you just need to throw something quickly together, that might not be the best thing to do.
Is that due to the compiler, or is that due to the lack of interactive tooling, like, for example, a Jupyter Notebook that you might have in Python?
Sorry, I didn't quite get the question.
I was saying, on one side, yeah, of course, the code will not compile until it's 100% correct. Instead of dynamic typing, you can get away with like some missteps along the way. But often what is raised is that in Python, you have tools for doing interactive exploration, like, for example, notebooks, which are generally appreciated by the scientists. Is there a major roadblock? Is that an okay roadblock? We don't really care. What's your viewpoint?
Depending what you're doing, right? Like, for example, I'm even weirder. I don't even use the IDE. I use a text editor to write Rust. It's really depending on what you're doing. If you're doing a lot of quick prototyping, maybe you should pick a language that kind of is supportive towards that. If you're about performance or correctness, Rust is the way to go. But I don't do, or at least I don't do a kind of data science research through Rust.
Understood.
Just to jump in very quickly, I've just been notified by the ODSC that we have time for just the last 2 questions. We've got a couple more minutes left. The actual seminar will end, as in I think the software will kick us out in the next kind of few minutes. So we have time for just the last 2 questions, and that'll be that. But what I would want to say is that we can please carry on this conversation in the Rust Discord. So we can treat that like the after me up drinks. We can all go to the Rust Discord and carry on there. where the speakers will also be in a Discord channel, and we can continue asking questions there. So if attendees want to come over to the Rust Discord channel, we can carry on there, but we have time for just 2 more questions.
Perfect. It's like the real meetup. You get kicked out at a certain point. So the one from Brewable. Daniel, do you have any plan for an alternative to Kaldi software you mentioned?
So I do keep mentioning at work that they should let me write an open source version to Kaldi and pay me to do it in Rust. We'd need to hire a few more people just to deal with all the work we've got coming in to free some people up to do that. But I would like to do it. But there's a lot in Kaldi. It's years and years and years of engineering work. So maybe not all of Kaldi, but I'd like a useful subset in Rust.
Amazing. And very last one from me then. What would you recommend as learning resources for getting started with machine learning if you're a beginner? I guess this is open to anybody who's willing to pick it.
A small interesting problem you have and that you care about. That's the most important thing, because then it's easy to find the resources to learn. And whether that problem is something, I don't know, from machine vision, you want to do something with your camera or with Raspberry Pi, some small app or some classification for something on the job or something. But a problem you care about is the thing that makes it easy to learn around it.
And I guess on that note, we wrap up. So as Ernest said, you can find us on the Rust Discord server. So any conversation that you want to have with the speakers, you find them there. For anything else, thanks to the speakers again for coming here tonight. Thanks to the people who attended, and I hope you had a good time.
Amazing. Thank you all very much again. And we look forward to seeing you in 2021. Thank you again to the Rust ML working group. Thank you all to all our speakers. And we look forward to just learning more and seeing more of what you guys do. Thank you.
All right, and thank you to the Rust team for this session.
Thanks, everyone. Bye.
Thanks all. Bye-bye.
Bye.